No more Afghanistan.
It's just so you know.
It's just a cool story.
Okay. So, Carolina, if you have any questions, just shout at me.
Okay.
Yes, because I won't be able to see like a raised hand or anything like that.
All right, no problem.
Cool. All right, and can you see my PowerPoint?
Yes.
Sweet. Alrighty. So, I guess if you have any questions, interrupt me, or if you have any questions like right now, you can feel free to go and ask any of those. As far as an actual agenda for tonight, I've got 2 problems. Very derivation based with Navier-Stokes. So he gave me like a solution, but I tried to go through and like fully derive everything so that you could see why you get the simplified forms you get. So I have a little bit more than he gave me to try and make it clearer for those, because like Navier-Stokes is like when I took advanced fluids, that whole class was just Navier-Stokes. Yeah. Just like stepping through different scenarios, and so it's pretty good like moving forward to know those. But subtitles, no thank you. Sideways. So are there any questions before we start?
What are the odds you can solve the entire exam he gave us today and have it graded for us?
And just grade the one that I I probably would not be able to solve it, like, I mean, maybe in a whole hour or hour and a half, but I haven't even seen it, so. All right. No, I have my Word set to dark mode because I just like it better. And so he gave me the problem in Word, and so I snipped it. It's just, yeah.
I don't even know what ChatGPT is. I'm such a good student.
Not read my papers.
Carolina, did you have any questions before I get started, or are you good?
I'm good.
Cool. All right. So, this question is, so this is kind of a long one, but I think that it's good for you to see like the full derivation. So feel free to stop me or slow me down or speed me up if you already know what I'm doing. But essentially we have an incompressible, that's important. Incompressible 3-dimensional velocity flow field that is defined as this. Okay. Now just write my little, I guess, unit vectors as hat vectors instead of the overbar vectors. But so we have that velocity field, and we want to know is continuity equation. Wow, I just wrote continued. Is the continuity equation satisfied? Or in other words, is it true when you plug in what you have? Is the continuity equation satisfied by that velocity field? Is it proven? Is it true when you plug it in? And then if you assume that gravity is given in the negative z direction, or negative g k hat, which makes sense, just saying it's going down, then if you assume that, and if you plug in your velocity field to Navier-Stokes, I'm going to abbreviate as NS, then do we get Bernoulli's equation? Okay. And part C, show that the flow field is irrotational. Okay.
What is irritation? Just like it's not rotating at all? Or
Or does that have to do with vorticity?
Irrotational, I believe, means that we don't have like any swirling motion.
So
I have to Google it.
would that either be vorticity or would it just mean that we only have like two like motions? So it's not three-dimensional motion. Like it would just be like I hat, J hat, J hat, K hat. Like it would just be moving in a two-dimensional sense rather than a three-dimensional sense.
well, can it still rotate on that plane?
Like on its own axis.
No, IJ, like it was just a plane. It's still rotating.
So what Gemini says is that irrotational flow is a type of fluid motion where fluid particles do not rotate about their center of mass as they move. So mathematically, it means that the curl of your velocity field is zero.
And the curl is the vorticity.
The
I thought that just would mean that your vector field would be.
your velocity vector field,
Yeah.
the curl of that is zero for your rotational flow.
We'll get there.
Yeah.
So I have,
Well, yeah, good.
I have one more question. So how do we identify if this is like a steady flow or not? Do we add that to the list of finds?
Could we add that to the list of?
Well, if it satisfies the continuity, isn't it a steady flow?
I guess I don't think I used steady flow, but you don't need it in this problem.
I asked because
do it.
in the homework, yes, is this a steady flow or why? So I was wondering if I could, like, with this problem, see an example of the logic.
Oh, he just said it is steady, or he asked to prove it basically. Well, as we go through, I'll try and explain my reasoning behind the assumptions I made. Yeah, let's come back to that question as we go through, because maybe it'll, as we talk about it, maybe it'll make sense. Okay, so okay, so continuity equation is this. I think this is a row there. dt d. This is dx. Okay. I'm just checking something about my logic super quick. Yeah, okay, I did that right. Okay, so this is the continuity equation. So what I said is that we can, I guess, simplify this, right? Because since we're talking about incompressible flow, then density is not going to change with respect to time or space, right? So I guess if you had a compressible flow and it was steady, you could say that d rho dt is 0. I said it was 0 because if it's incompressible, then okay, well, let me write. Here we go. And that's 0. And then also you can factor out the rho and divide that over. So I basically reduce this down to ddx u plus d dy v plus d dz w equals to 0. And that's because we have incompressible. So no change in density with respect to time and space. So then d rho dt equals 0, and you can factor rho and divide over. Okay. So with that in mind, then we can plug in our velocity field. So we have d over dx, and then plug in the x component here. That's our u, kx. So here we have kx plus d over dy. That's u. This one here is v, and that right there is w. So this is kx. I'm sorry, ky. My bad. Ky. And then plus d over dz of negative 2 kz equals 0. And then when we take the derivative there, we end up with k plus k minus 2k equals 0. Or in other words, 0 equals 0, which that is true. So yes, continuity is satisfied. Let me mark that. That's part A. So I guess to answer your question, the way that I interpreted this is that d rho dt is 0, not because it's steady, but just because it didn't specifically state that. I was just thinking that if it's incompressible, then density won't change with time or space.
Yeah.
And so that's why I did it that way. But
Yeah. So in the homework, he has like part A is this flow steady y, and then part B is this.
okay.
So I was just trying to like figure out the conceptual as to why it would be.
Yeah, because
Steady.
in his lecture, he said that in the case of steady flow, d rho dt is equal to 0, but it can be steady whether it's compressible or incompressible. And then he said in the case of incompressible flow, d rho dt is always 0 regardless of whether the flow is steady or unsteady.
Mm-hmm.
So I guess what I was just kind of curious on is like how do you like identify it being steady versus unsteady? Like what's the deciding factor of if it's steady or unsteady, I guess.
I'll have to
Yeah.
ask him. I'm not sure looking at this how you would tell.
Yeah, that's pretty much like the same exact scenario we have
Okay.
for our homework questions. So.
Yeah. I mean, I guess maybe one way you could tell is when, so the question was, looking at this, can you tell if it's steady or unsteady? I don't know if you could hear them, Carolina, but they had a question about looking at this, can you tell steady or unsteady?
Yeah, I wouldn't be able to tell. I'll be cooked. Nah, it's cool. Any time on the test I don't know something, I'm just gonna be like, I'm gonna assume this is steady.
Assume it's, I mean, that's not a bad strategy. Just,
So we didn't do that today.
that's, yeah, I mean, it's like if you don't know, just make an assumption, keep on going.
It's been this
I love
the
that.
experience this whole class.
Assume gravity is like probably like 12 or some shit.
You define it, it's true.
So what I was going to say though is that looking at this, if you notice in that velocity field, time doesn't show up anywhere. So if time is not a factor in your velocity field, then that to me would indicate that it's steady, because time is not even a consideration.
Yeah. So because time isn't in and out, because I'm just gonna show you this real quick, just so you can see like what he said.
Yeah.
So the top one, this one is steady here, and it's
Uh-huh.
with rho still in the equation. And with rho out of the equation, he says that's for when it's incompressible. So he says that this one can be compressible or incompressible. So it's pretty much the same exact function.
Mhm.
It's just the only difference is that that one has density in each of those factors still.
Yeah, right. And that's
So-
just because that density, that's where I factored it out.
Yeah,
and
exactly.
divided
And the
it.
thing
Yeah.
is like you can still have it be steady but be compressible, right?
You can.
Okay.
Yeah. It can be compressible and steady.
Gotcha.
Right. Yeah.
I understand.
So that would be my thinking on that. Time doesn't show up. Okay, part B. Welders make some good money.
We're talking about that. The underwater ones?
They do. Pilots do too.
I wish I had that down payment for a plane.
Yeah. Okay, so part B. Okay, what I'm gonna do is I'm gonna write out Navier-Stokes, and then I'm going to apply the simplifications to get to the form that he gave me, and then go from there, just so you can see like the full thing. So this is Navier-Stokes. Okay, X component. So we have, are you pretty familiar with Navier-Stokes?
We did it today.
Did it today? Okay. Well, this is good. This is good practice, because you'll see this in, like, if you go on to more fluids classes, this will show up a ton. This is basically what my research is. Like CFD, all the CFD does is solve Navier-Stokes. Yeah, that's all it does.
Which I feel like is pretty recent, right? That they got like software that could do that. Like, I mean, like in terms of like the field, it was like 20 years ago. They didn't have that.
Right. Yeah. I mean, I think they've been doing CFD for a while, but computers have only gotten powerful enough to actually crunch through the numbers recently.
That's crazy.
So yeah, and that's why like what we use in the lab are so powerful, because you kind of have to have that to be actually be able to just have the horsepower essentially.
Yeah, that makes sense.
DUDYV. Okay, DUDZW equals 2. Now this is pressure right there, not density. So dP dx plus mu. And this is d squared u dx squared plus d squared u dy squared plus d squared u dz squared. Okay. And then plus rho gx. Y component. Rho dv dt plus dv dx. No. That's a U. There. dv dxu, yes, okay. And then dv dyv plus dv dzw equals to negative dp dy plus mu d squared v dx squared plus d squared v dy squared plus d squared v dz squared plus rho gy. And z component is rho dw dt plus dw dxu plus dw dyv plus dw dzw equals to negative dp dz plus mu d squared w dx squared plus d squared w dy squared plus d squared w dz squared plus rho gz. Nice. So that's familiar. Okay, cool.
That's for sure.
Do what?
You've seen it, that's for sure.
That's good. That's good. Awesome. Okay, so all right, now that we've looked at that, I'm going to start marking stuff out. So, all right. Okay, yeah, so just like I mentioned earlier, when I said there's no t in the velocity field, if you took the derivative and it was first the du dt, dv dt, dw dt, if you took derivative with respect to time, oops, right, those would all three go to zero, right? So because of that, 0, oops, 0, 0, 0. I believe so. Yeah. It's been a while since I've heard the term, those terms for them, but that sounds right.
Yep, so those are your
Yeah.
local, and then everything with U, V, and W are your convective.
Convective terms. Yeah, that sounds right. So this is because no t in the velocity. That's how I explain that. Then we have, okay, so then we have du dx times u, which is a valid term because if we look back at our velocity field, our u term has an x. It varies with x. But that u term does not vary with y or z, right? So then this guy is 0 and this one's 0 because no y or z in u. Then we have dp dx, that's valid. And then we have these three terms on the second derivatives. So these two are 0, again, because no y or z in u. Or, another way you could say that is, no dependence on y or z of u. However you want to look at that, based on variable or based on like physical significance. Then this is 0 because no x gravity. Gravity's only in the z direction. And then this guy, du squared dx, that is 0. But that is because if you took a second derivative of kx,
0 is a constant.
then you get 0, right? Yeah. So, well, this is just good because like there's so much happening all at once that like I think it's good to like step by step go through and be like, why is each thing?
I also think it's important just to like write out the whole thing every time. Like even when I was doing problems on the exam that I'd already like done a lot, like I always write out the full formula.
Yeah, exactly. That way you can kind of like see everything going on, apply your assumptions, and then move from there.
Computational mistakes that way.
Yeah, exactly. I agree.
Please, I wrote a bunch. Give me partial credit. I know I got -9 million for an acceleration of a plane taking off.
Okay. So same logic applies to these. That dv/dx term is 0, and this one's 0 because there's no x or z in v. Same logic here, 0, 0, no x or z in v. This is 0, no y gravity. This one is 0 because the second derivative equals 0. Yeah, I think that's it. And then this one, we have 0 here, 0 here, because there's no x or y in W. These are 0, no x or y in W. This is 0 because the second derivative equals 0. But then that gravity term does stay because we do have z gravity. So any questions about those, the application of all those assumptions? Cool. So with that in mind.
Can you go back really quick just so I can take a picture?
Yeah, sure.
Think you got it.
Yeah, sure. Okay. So now, after all that, what we end up with is rho du dx u equals to negative dp dx. And then we have rho dv dy v. Yep. Equals to negative dp dy. And rho dw dz w equals to negative dp dz plus rho gz. Cool.
That looks a lot better.
It does. Much better. Okay. So we can go and plug in some things. So this is going to be rho d over dx of our u was kx, right? From there. So then that's that. Negative dp dx. And that's going to give us rho k. Oh, I'm missing something. Yeah. Go. What were we going to say?
I was gonna say, isn't it du dx times u?
It is. I was wondering why I was missing something. It should be that right there. Good catch. Thank you.
He actually made that mistake on purpose.
I did. That was a test. That's exactly what that was. Okay, does that look right? That's what I have on my paper now. Cool. Then we have rho d k y dy ky rho k ky dp dy, and then we have rho. This was negative 2kz dz. And then I'll write down here. So this would go to rho negative 2k negative 2kz dz, or 4 rho k squared, which technically, I guess I'll write it like this: 4 rho k, just to be consistent. But basically, in each of those expressions, you'll end up having a k squared, right? So, okay, but I'm just gonna write it like that so it's consistent with itself. Oh wait, and there's a rho g here too. Okay, then we have this plus rho g, but g is stated to be negative gk, so that's why there's a negative. That's that negative gk. Okay. So what we're trying to do is get Bernoulli's equation, right? So we're going to do that by integrating these guys. So if we integrate the x1, okay, the x portion, what we're going to get is p of x is equal to negative, I just moved the negative over in the top right there. So we get negative rho k squared x squared over 2 plus a constant. I'm going to call it px naught. I guess usually this would be like a c, right? Like in calculus, we call that c. But then if you applied like a boundary condition, I guess you could think of that as being your initial pressure.
In class, he did FYZ.
FYZ.
Yeah.
Or FXZ. Wait, FYZ.
It was YZ because if we differentiated it, it'd be 0.
Oh, because it's a function of the other two variables. Yeah. I see. Okay. Okay. Yeah, in his solution, he denoted it as P naught. Okay. He denoted it as P. Like that is how he had in his solution. And so I kind of took that as that constant is like your initial pressure, something like that, physically. So like after you apply boundary conditions and that kind of thing. So yeah, that's the only part that he denotes it, I guess, one way in class, FYZ. And then he gave it to me like that. So my interpretation is like initial pressure.
But all the same thing.
That's my understanding. Actually, what I might do is I might just run that by him, that question, just to double check my my explanation there. I didn't have time to meet with him today, so
It's okay, you don't have enough time either. It's a busy part of the semester.
yeah, he's super busy for sure.
Everyone gets slammed around this time of the year,
Exactly.
especially with hurricanes.
Yeah, exactly. So I'll say, okay, question. Initial pressure. Okay. So, then our integration for our y is going to be P of y is equal to negative, we'll get rho k squared y squared over 2 plus some sort of like initial y pressure, something like that. And then our z is going to be, right, we're going to get negative, and this will be 4 rho k squared z squared over 2 plus, we have this, I guess it's not plus, it's minus this rho g z, integrate the rho g term, plus some sort of initial z pressure. Okay, so that's that. Now, if we were to combine those together into one term, so here I'll say we're combining here, then, and so here we're looking for pressure x, y, z, all 3 dimensions. Then what we're going to get is I'm going to pull out the rho k squared over 2. And then that's just a factoring thing there. Then here we have x squared plus y squared plus 4z squared minus rho gz plus, and this is that kind of like initial pressure term I was talking about, P0, 0, 0. That's what I'm going to ask about. So that is Bernoulli's equation. It doesn't look like it though, so I'm going to rewrite it to look like Bernoulli's equation. And the way I do that, I don't know. And the way you rewrite that is keeping in mind that, right, Bernoulli's equation is like this. Over 2g plus h, or I'm sorry, plus z1 equals to p2 rho g plus v2 squared over 2g plus z2. This is what we're used to. So then if we take what we had before, we can recognize that if we said k squared, if we distributed that k squared back through, wouldn't that be this kx term squared? So if u is kx, and here we distributed that k squared to that x squared, that would just be u squared, right? We could just rewrite that as u squared.
Yeah, that makes sense.
And then v squared and w squared.
Yeah.
Right. So then this would go to, so basically we rewrite this as p x, y, z, plus rho divided by 2 multiplied by u squared plus v squared plus W squared plus rho G Z. I kind of moved some stuff around too. So I took some of the negative terms over to the left-hand side and left that kind of P naught on the right-hand side. And then yes, okay. So then I guess what you could do then is you could say like, and this is part of what I'm going to confirm later, is the significance of that P naught term. But I just divided that over and said that I'm not divided. I subtracted it over. And I said basically this is like maybe like a gauge pressure is maybe the physical significance of that. Like if P naught is like, let's say atmospheric pressure. I'm going to confirm that though. But I'm just going to call that for now gauge pressure, because I think that's the simplest way to do that. And then this is rho over 2 U squared plus V squared plus W squared plus rho GZ equals 0. All right, now all you do is divide by rho G. So I'm going to call this P prime. Well, maybe not prime. I'll call it like P star, because prime might look like a derivative or something. So P star over rho G plus this guy here is V, right? This is V over 2G plus Z equals 0. It does. Once you rewrite it, it's like, oh, okay, so that it is Bernoulli's. It does look like it.
I initially thought that like first step was what you were gonna write as like the final. I was like,
Like, how'd you get there? Yeah, no, that's just for comparison. Yeah. Cool.
Yeah, so for the P like 000 makes sense.
Mhm.
He was doing a different problem in class that started in the same way,
Mhm.
but he was doing it where he found that unknown function of y and z, and then it became f of z, and then he found that unknown function to find the whole like pressure
yeah,
gradient, I guess.
so he kept on going.
This makes sense.
Okay.
Yeah.
Yeah, I mean, I guess this term here is found by your boundary conditions. Because like I said, when he gave me the solution, that was just given as a part of the solution. And so all the derivation up to here, I just did myself, because I figured it was like helpful to kind of see that results from the integration process, at least as far as I can tell, based on how I worked it. So, yeah, but I guess that is a constant of integration, that when you apply your boundary conditions, you end up with this like pressure term. Okay. That's my understanding, but I'll confirm that with him.
I'm mainly curious about the gauge, like if you
like it. Yeah, so maybe I shouldn't put gauge pressure. I'll just call it P star. That was just that was the only term that came to mind for me when I thought about like, right, because gauge pressure is absolute pressure minus atmospheric pressure.
Yeah.
So that was just what came to mind, is like, what do I call this pressure term to make it make sense to me? So I'll just leave it as P star until I confirm with him about what the physical significance of that is. But I'll just call it that just to make it mathematically look clean. So. All right, part C. So irrotational flow. So irrotational flow is defined, we want to, I guess, determine if it is irrotational. So if you take the curl, which is del cross the vector, or velocity field in this case, then that is defined as, we're taking this cross product, or you could think of that as a determinant to d over dx. So this guy, this row here, that's del. Then this is that.
Oh, this is the curl thing, right?
Yeah, this is a curl.
Okay.
The curl, I guess, of the curl of the.
Does A have its own curl? How does that work?
Hey.
Like acceleration? Would acceleration have a curl?
Yeah, so a curl is a mathematical operation.
Okay.
So curl is like saying you're taking the derivative of v. Derivative is an operation on v. Curl just means you're crossing whatever vector you have in mind with that ddx, ddy, dz.
I think it changed the, if I remember correctly, this is from Calc 3, so this may be wrong, but it changes the vector, or the like vector field too, doesn't it?
That's going way back for me. Yeah.
I feel like I remember like the vector field would be like go from being like linear to like non-linear.
Okay.
I have to like
Okay.
look it up. I'll look it up after this and figure it out.
Okay.
I think I know. What I'm talking
It does change the vector.
about. Yeah.
Yeah, because you're basically, when you curl it, when you cross it, you're going to end up with a different vector than you had. And that the difference, as we'll see here in a second, is like this kind of derivative.
So it's going to be an order lower than your original one.
So it's like an instantaneous change of direction for the vortex, I guess?
Yeah.
Is that what it is? It's like, it's the slope,
Mm.
I guess, as it's coming off
It's the slope of
the
the
steady
steady.
part of the flow.
I'd have to ask Dr. Vassal that. So you want to know, like, what's the physical representation
Yeah.
to the?
That's pretty much how we make all the connections.
No, that's good. That's good that you're doing that. It's been a little while since I've thought about the physical significance of a curl.
Well, don't worry, we've never thought about it until now. So you're doing it. You're already a step ahead.
Significance.
Just the interval of 1.
0.
Okay. So, okay. Cross product. What did I call that earlier? Determinant. Yes, that's what it is. So, right, this would be d dy of that guy minus d dz of ky I minus d dx of that minus d dz of kx j plus, that one's a positive, positive, negative, positive, d dx of ky minus d dy of kx. Okay. Right. And then conveniently, if you notice the derivative, each of these derivatives is of something that's not in the term. So this is 0. There's no y in that term. This is 0. This is 0, 0, 0, 0. Yeah, he's got to remember the cross product exactly. And then cross.
We did it in dynamics. In statics. How did I get these in this classes?
Because Lauren is still fearing our bodies.
I wasn't confused. Just ask me something. That was so.
I'm gonna Google. and look up
So,
the curves.
Makes sense.
For irrotational, I know we talked about it before, we just mean there's no vortices.
I believe so.
Okay.
I think
Oh, okay, that makes way more sense. In fluid dynamics, curl is the tendency of a fluid to swirl around a point. Okay, that makes a lot of sense.
wait, what is curl?
Curl is the tendency of a fluid to swirl around a point, according to Whitman.edu. So it has to be right.
Okay. That's good to know. My understanding of irrotational flow, I'll double check that as well, is like if you had a pipe flow, it's not like spinning in the pipe. That's my understanding, thinking back. But I'm gonna double check that just so that I'm telling you correctly there.
And vorticity is the curl of velocity.
So would that mean it's like a steady
Okay.
flow with laminae? If there's no like.
Wait,
if
that
it's all
actually
going
does
in
make
one
sense.
direction?
That actually does make sense what he said. You're looking good.
Yeah, if vorticity is the curl of velocity, and that's 0,
It has
So
to be steady, right?
no vorticity. Well, that would mean there's no rotation
Which
stuff.
means if there's no vorticity, is there no turbulence?
I guess that
You
means,
still have
right.
turbulence without vorticity.
No, I guess that means there's no turbulence.
Because if there's no turbulence, then that means it's steady, right?
It doesn't mean it's steady, because steady just means it's not evolving with time.
Oh,
So you could have like linear flow that's still changing with time.
so it's just like a laminar flow.
Right, I think so,
Not a
yeah,
steady flow necessarily.
right.
Okay.
I don't know if
That's
you
my
agree
understanding,
too, Chance, but Science Direct said that vorticity is the curl of velocity, so this is vorticity.
Okay.
So we're trying to find when the vorticity is equal to 0,
Yes. Yeah.
like a bomb.
I like this stuff more than the last exam.
It's 'cause
This stuff actually gets interesting, because at least when I took advanced fluids, this is where it started to go like, okay, I see how this is all coming together. You know, for like, if you gave me a flow problem, I see how this is kind of like describing what's happening
paint a
more.
picture in your brain.
I like this type of math.
Right, man.
Same.
Cool, man.
I like the double.
You're not wrong. I mean, here I am. So, okay. Next problem, I guess. So we only have a couple minutes left, but I might be able to still like super quick go through this last one. Okay. We have a channel, vertical, fluids going down through there with just gravity, no pressure gradient. The plates are 2H apart. It's fully developed. So that means that the velocity in the Z direction only changes with X. Okay. What that means,
Does that mean it's based on like the boundary? What's it called? What's the
Boundary condition, no slope.
Yeah, the no slip condition. Is that what it means?
this does have no slip. What it means is fully developed. Think of it like this. If at time 0, you had that, as you progress down the pipe, it stays the same. Yeah, it doesn't look like it, but It's- yeah, it's the same. Not fully developed would mean you have like, you know what I mean? Like as you move down the pipe, it's changing.
So I hate to ask a conceptual question. 2 minutes left, but
No, you're good.
so
I'll just do this later.
Could you have something fully developed and have vorticity present? Because it's hard to like imagine like just like logically like how you could have vorticity and have a fully developed flow.
Could you have vorticity?
I know that's kind of a loaded question.
I'll ask that too.
Okay.
Yeah. Because I guess if you had like,
If your vorticity
Like-
was constant too, you had a value, if that's possible.
right, like if you thought like a mixing bowl,
Okay.
you know, like
yeah.
you were mixing
Where
like
it has,
batter
a
or
central
something.
axis.
Right. Then it's like, if it was moving around that center,
Gotcha.
then I guess that would be like a constant vorticity.
Gotcha. Okay. That makes
Yeah.
sense. That's a good explanation.
Yeah, I think that, yeah. But I'll ask that too. And we're basically out of time, so I'm just gonna do next week's recitation. I'm gonna be traveling, so I'm just gonna upload a recording.
You gotta do
I
it
know.
on Wednesday for Thanksgiving week. That's messed up, man.
Do what?
You gotta do it on Wednesday for Thanksgiving week.
Well, yeah. I'm gonna record before I leave. I'm gonna record it and then leave.
Oh, so you don't have to do it. I'll talk to Dr. Bass.
My week is rolling now.
Yeah.
What was the question? Can you have fully developed?
A lot of questions today.
That's good though. That's good. I mean, this stuff's so heavily conceptual that asking these questions is good because you're like hopefully gonna actually understand it more thoroughly, you know, afterwards.
That's
So
pretty much the goal. I feel like it's a lot easier to approach problems like new scenarios when you have a better idea of like what's happening logically versus what's happening mathematically. 'Cause
Exactly.
Anyone can follow the math. That's not hard to do. But
Right.
following the logic behind the problem is the part that you like really need to understand.
exactly, yeah. And that's why I wanted to step through that whole derivation, even though it took forever.
That was super helpful.
You know,
though.
I hope it was helpful.
It was
Yeah.
super
It's gonna help a lot with the homework. That one is just straight derivation.
Especially that vorticity part, like for like trying to figure out, I think there's gonna be a way where we're able to relate like vorticity did.
Mm.
We'll have to see. We're gonna work.
Carolina, did you have any questions before I shut this down? Or are you good?
No, I'm good.
Cool. All right. Well, have a good night.
You too. Thank you.
Yep, of course.
You're in the wall.
I thought vitamin G that
You're in the walls.
Can I help on the camera? Did KJ send me a
Ooh.
Oh, shit.
There's a ghost.
But no, yeah, with Batman, she's in there. KJ like hopped in the mic while we were at Checkers, and she sent me a picture of them, and they literally were both looking up at the camera, and they were like, I couldn't believe that they were real.
The voices, they're not just in my head.
Alrighty, Devin. Well,
All right, guys.
you enjoy your Thanksgiving break.
Yeah.
Have fun.
Are you going back to Tennessee?
I am.
It's gonna be
Yeah.
nice as fuck there right now.
It's
All the
like
pretty trees,
40
weather.
degrees every day.
It's okay, I'm surfing.
I was like, oh, are you? Okay. There you go.
Florida Thanksgiving.
For surfing and
Surfing and
warm.
steaks and beers.
Some Ronas and steaks.
Maybe next.
You-
Roasting us.
You didn't hear that.
Y'all have a good one. Yep. See you.